All right, I'm restarting this recording because I thought I had done the first problem incorrectly, and then I looked at the answers, and then I was like, oh no, I was doing it right. I just didn't realize it was going to go out of bounds. Okay, so this is question 2 from the set of Unit 10 problems that I assigned the other day. We did number 1 together already, so again, we're jumping right into number 2. This involves extracting values from a 2D array. The initial call is to mystery23, so I've already written that above here. If the row is not 0 or the column is not 0, if either one of them is not 0, we're going to make a recursive call. So first we take the value at position 2, 3, which is 11, so that's why I've written 11 right there. We're going to add that to the result of calling mystery again with r minus 1 and c minus 1. So we go from mystery 2, 3 to mystery 1, 2. Mystery 1, 2 then calls mystery 0, 1 and also adds in the value that's at position 1, 2. And then mystery 0, 1, since the if statement is formatted such that it says if r is not 0 or if c is not 0, if one of them isn't 0, we're going to keep going. So 0, 1 actually calls negative 1, 0. And it's going to go out of bounds because we reach some negative indexes, and no matter what, we're going to add position RC or access position RC. So the answer is it goes out of bounds. Okay, number 3, we're dealing with string values. The initial call is to rec scramble with the word epic, the set of indexes, and 0. All right, if the string is null or the length is 0, we're done. If the string is length 1, we return the string. Neither of those are the cases. Those are the base cases. All right, so we get an integer value, which is positions k. The k value is the last parameter. So our position value for this call is 2. It's the first value from the indexes list. We make a string called inString, and we assign it the substring from position to position plus 1. So of the word, so since the position is 2, we have 0, 1, 2. So this string gets the value of I from epic. And then we make a variable called string, or we're going to reassign the value of string and get position substring 0 to 2. So that's going to get us EP plus substring position plus 1. So that only has one parameter. So we're going to start at 3 and go to the end. So in this case, it's the letter C. And then we're returning what was the point of doing that? Oh, okay, that's the string that we're going to send to the recursive function. So the value that we're ultimately going to return is I, which is the in string, plus the result of calling rec with EPC, the same set of values, and the number k plus 1. So then in that case, that's 1. Oh boy. All right, iteration number 2. This is going to be gross. So we have a 3-letter word this time, EPC. Okay. This time the position is 1, or the k value is 1, and so we get the value that's at index 1 of our array, which is 1. We make a string, in string, that gets a value from our parameter here. 0, 1. So P is the value that we get. We make a new string. We make our new string out of 0 to 1, which is the letter E. And then 1 plus 1 is 2. So 0, 1, 2. So that's going to get us C. So string is EC. And then we call the function again, and it's going to return P plus the result of calling the function again using EC, the same set of numbers, and 2. All right. All right, let's run it back. This time we're at positions 2. So that is the number from our array, which is also 1. We make an end string, and it's a substring from 0, 1 to 2. Did I do that wrong last time? I did 0 to 1. Should have been 1 to 2. So, no, that was right. Yeah, I got the p value. Okay, so end string is again 1 to 2, so that's the letter C in this case from EC. And then we make a string value. This time it's 0 to 1, E, and then value 2. So that'd be nothing. That'd be the empty string because there's only 2 letters in our string. All right, so then we're going to return C plus call to this function with just the letter E. And I already know that function, since it's of length 1, is just going to return E and not call a recursive value again. So the result of this is literally just CE. And then we're going to add that to the return value of our previous ones. So P and I. I, P, C, and E. So IPCE is the final answer. Okay, this is a much quicker one. The purpose of this function is to find the maximum from an array, and instead of using a for loop, it calls the function recursively and just changes the starting value. The key here is looking at the base case. The base case is basically, are we at the end of the array? So if the start value is data.length minus 1, in other words, are we at the end? We're going to return that value that's at the end. Otherwise, if we're not at the end, we're going to check to see if val is bigger than data start. And so the question is, well, okay, what's val? Data start is the current position that we're at, and we need to see if something is bigger than that. Okay. So the answer is C. We need to look further down the array, and so we're going to call the maximum function again, and that maximum function is just going to keep working its way down the values in the array. And each time we're going to compare it with the current value in the array that we're looking at right now. And if it's bigger, then we'll return that value, the bigger one. And if it's not bigger, we'll return the current one. Okay, here's a question about using binary search to find a value in an array. The trick with this one is we're looking for the number 70, but there's a lot of 70s in the array. So the question is which one is it going to find using the algorithm? So the initial values for low and high are 0 to 8. This is our window that we're going to narrow down. So the first thing we do is we find the average of those two numbers, which is 4. So we're going to go 0, 1, 2, 3, 4. We're going to look right there and see if that is 70. It's not. So we're going to go higher, And so our window is gonna, instead of 0 to 8, so I'm gonna write down the windows here. Instead of 0 to 8, now we're gonna go 5 to 8 because the middle was 4 and we're gonna go past the middle. All right. So with 5 and 8, the middle of that, 13 divided by 2 rounded down is 6. So 0, 1, 2, 3, 4, 5, 6 right there. And that's 70. And so that's the answer. It returns 6. We're done. All right, on number 6, I thought this was the hardest one to think about. When I was doing it originally, I think I should have done like an actual example problem, like using the array that we just went through for the previous problem. This is a binary search, so you should recognize that. It's doing the same process of finding the middle value and then seeing if that middle value is too high or too low. And so the window changes just like it does with a binary search. How this one is different is that instead of returning -1 if the value isn't found, it returns the index at which we would be when the window closes. Okay, if low uh, eclipses high, that means that the window is closed, and it returns that low value. If we find a match, it returns the position of the match. But again, if it's not found, it's going to return the position of low. And so what that means is since the array is sorted, because it's a binary search, that whatever position that it returns, whether it's found or not found, that's going to correspond with how many numbers are in the array that are less than the number that we are looking for. All right, number 7 is a merge sort example. I'm really pleased to see that the two people who have done this problem so far got it right, because this should be one that we should be able to get right based on what we did in class on the merge sort. I mean, you can read through all this garbage here, but ultimately it's like, short story is it's merge sort. So I don't know. I wouldn't even bother reading through most of that. The important thing is we start with an array of 6 values. Merge sort cuts that in half into groups of 3, and those groups of 3 get cut into groups of 1 and 2. When you get odd numbers, you have to split them up unevenly. It doesn't really matter. Ultimately, the groups of 3 are going to get pushed back together and merged in order, and so we have 30, 50, 80 for the left half, 20, 60, 70 for the right half, and those get merged back together in order. So the correct answer is D. You just need to recognize the left half, right half pieces there and how they are already ordered so that they can be merged together in the final order. Okay, for this last one, it's the same setup. It's merge sort again. They're asking you how many times will merge be called. We didn't talk about this aspect, but we talked about how merge branches because it does left half, right half. I didn't really explain the part where merge itself, the filtering back together part, is a separate function usually called a helper function. But in order to solve this problem, you basically need to recognize that merge gets called once every time the recursive function is called. Right? Merge gets called once every time the recursive function is called. So the original function is for 4 values. Those 4 values get split into groups of 2. Okay. So we're going to call merge on each of those groups. And then those get split into groups of 1. But we don't call merge on the groups of 1. So ultimately, we have a merge call for these 2, we have a merge call for those 2, and then we have a merge call for when they get all put back together as a group of 4. So it's a total of 3 mergings. You don't have to merge the single values. That's why it's not a larger number. This is basically the same answer for like when we were doing the guessing game, too high, too low. If there were 4 numbers and I had to guess too high, too low, how many guesses would it take? It's the same answer, 3, because of how many times you have to split up the groups.